Good morning. Today we are going to talk about log functions, the second part of chapter 12. Let's start with page number 1 of your L19 packet. Make sure you have access to this before you start this video. If not, you could pause this video, either print it out or download to your computer or tablet. First page is about the need of having log. Why do we need to have this log function? So let's actually look at these. These are basically equations that they ask you to solve. So we're going to use inverse operations to solve. The example they gave us is x plus 3 equals 12. It's a very simple linear equation. The operation on our variable x is addition of 3. To solve for x, we isolate variable x by performing inverse operations. The inverse of addition of 3 is subtraction of 3, so we subtract 3 from both sides and we obtain x equals 9. That's basically the essence of solving any kind of equation in algebra. You perform inverse operations until you isolate your variable x. Number 2, 3x equals 12. The operation on x is multiplication by 3. It's multiplication by 3. So the inverse operation will be dividing by 3. Therefore, we're going to divide both sides by 3. And that's going to give us x equals 4. Number 3, x cubed equals 12. The operation on x is something raised to the third power, which is cube. As we know, the inverse operation of cube is cube root. Therefore, we perform cube root on both sides of the equation. Cube root on the left hand side, cube root on the right hand side. On the left hand side, the cube root and the cube cancel out, so we have x. On the right hand side, we have cube root of 12. And that will be our solution. 12 is not a perfect cube, so you cannot simplify that. Simply leave it inside. Number 4, 3 to the power of x equals 12. The operation on x, some of you might say that the operation is just the same as number 3. It's cube. But is that cube? If it's cube, the 3 has to be on the top right part. Our 3, number 4, is the base. So this one is actually not cube. What is the operation on x then? The operation on x is actually looking at the base 3, so it's power of 3. Power of 3. Or if you want to use notation, you could do raising 3 to a power. So this is the operation on x. However, do we know an inverse operation that can be applied to the power of 3? Do we? Well, at this point, at least we don't have a very clear one, right? So we can't solve this for number 4. Looks like we got stuck. Let's try other problems first. Number 5, solve radical x equals 12. This one is not that bad. The operation on x is that square root. The inverse operation of square root is squared. So we're gonna square both sides. Once we square both sides, left hand side becomes x, right hand side becomes 144, and we got our answer. Number 6, x over 2 equals 12. The operation on x it's a fraction, so you could just think of that as dividing by 2. Therefore, our inverse should be multiplying both sides by 2. Once you multiply both sides by 2, left hand side becomes x, right hand side becomes 24. Number 7, x raised to the power of 3 over 4 equals 12. This time we have a fractional power. Fractional power, if you remember from our previous discussion, the numerator represents the regular power raising to an integer power, and the denominator tells you the radical part. Our denominator is 4, so you're taking a 4th root. So if you want to do a step-by-step, you could do a step-by-step. The left-hand side is basically you're raising x to the 3rd power, the cube, and then you take a 4th root of that x. That's what the left hand side is. So you could break it down into two operations on x. First one is raised to the third power, and then you take a fourth root. To do inverse operation, you simply reverse each of them. And inverse operation, so if you remember, you have to do the complete opposite in the backwards order. So I'm going to do these little curves to help me identify the inverse operation. The inverse of fourth root will be fourth power, and the inverse of cube will be cube root. Therefore, the first thing we do is raising both sides to the fourth power. That's going to give us x cubed equals 12 to the fourth. So that's what we have. And then we are going to take a cube root on both sides. Once we take a cube root on both sides, the left hand side becomes x, and the right hand side becomes 12. And then you have another 12 left, because inside the cube root we have 4 12s. Since it's a cube root, you could take out 3 12s, and it becomes 1 12, and you still have 1 12 left inside. So that's why your answer is 12 and then cube root of 12. Number 8, 2 to the power of x equals 12. The operation on x, this one is very similar to number 4. It's not square or square root. It's a power of 2, because your 2 is the base and your x is simply the exponential part. So it's a power of 2, that is the operation of x. What is the inverse operation? Well, unknown. Just like number 4, we have no idea. So which problems are we stuck on? Apparently we stuck on number 4, number A, because we don't know what the inverse operation is. So unknown inverse operation. If you realize the title of this handout is actually related to the inverse operation that we're trying to find, then you know that the power of a number, the inverse operation, would just be the log. And that's basically the importance of having log. This is the definition. Assuming that we have a function f of x equals b to the power of x, where b is greater than 0, b is not equal to 1. So this is basically an exponential function. Since f is 1 to 1, you can actually graph it and see. We proved it last time that 2 to the power of x is 1 to 1. Then we can actually find out the inverse, and inverse will also be a function. So that is the conclusion that we got last time. The inverse in this case will actually be this. So you have that inverse notation followed by log base b of x. So that's basically how you pronounce this. You say log and then base b of x. So that's how you describe that. For example, if your f of x is 10 to the power of x, then your inverse will be log base 10 of x. You could just think about the base. The base in the original function is 10. Therefore, in the inverse, the base of your log function is also 10. So the base stays the same. And then the other part is just the x part. Even they have the same position, right? X is just to the right, top right of 10, your base. So that's one way that you could actually kind of remember how you find out the inverse of a power of a number. You simply add a log in front of that original function, rewrite the exponential function as the base, and the x will just be the top right of your base, and that completes your log function. There are also some properties that we can apply to log functions. Since we have that property that the function of the inverse is the original input, it's basically you undo what you just did. We have this property here as well, because the power b and the log base b, they're inverse operations. when you have expressions like this, right, b raised to the power of log base b of x, the base power b and the log b, they cancel each other out. So all you have left is simply x. Same thing with the other property. If you have log function outside and then you have the power of b inside, the log b and the power of b, they cancel out because they're inverse operations, and you have x left. Let's complete this table to actually get familiar with the exponential function and the relationship of its inverse. The first example, they already gave it to us. Function f of x is 3 to the power of x. Inverse is, first of all, it's a log function, and the base is still 3. It's the same base as before, and then you have the x, which is in the same position as before as well. So that's log base 3 of x. If you apply properties, we have 3 raised to the log 3 of x equals x, because 3 and log 3, they cancel each other out. Same thing if we have log base 3 outside and 3 to the power x inside. The log 3 and 3, they cancel each other out, and you have x left. Let's look at number 2. F of x equals 5 to the power of x. Inverse. Because it's a power of 5, your inverse will be log base 5. And the other part will simply just be x. If we apply the two properties and rewrite the expression, this one will be base is 5, and I raise to the log base 5 of x. Because 5 and base 5, they are inverse operations, you cross them out, and then you simply have x at the end. Same thing with the other property. If I have log base 5 first, and then inside I have 5 raised to the power of x, I can cross out the base log base 5 and the base 5 because they're inverse operations. All we have left is just x. So that's pretty much what this table is about. You have different kinds of exponential functions, and you could apply this property. We're just gonna do the one last problem, which is the last one. F of x equals 1/2 to the power of x. So the inverse is simply, first it's a log function, and the base of this log function is the same as the original base in the exponential function, which is 1/2 followed by x. To apply properties, first is the base raised to the power of log base, the same base of x. In this case, 1/2 and log 1/2, they cancel out, so you simply have x. Same thing with the other property. If we have log base 1/2 outside, and then 1/2 raised to the power of x inside, then in this case, we cross out log base 1/2 and 1/2, and then we conclude that there's just x left at the end. To summarize, we have these two properties, which comes from what we discussed last time about inverse functions. Let's do a little practice. Part 2. Circle the expressions below that simplify to be x. Please pause this video and try your best to find out the answer. Once you finish, restart the video and then check whether or not your answer is correct. Alright, hopefully you find out your answer. The correct answers are these three. These three will simplify to bx. Moving on to next page. Next page talks about the correct notation of exponential functions as well as logarithmic functions. You need to make sure that the operation for power of 2, that exponent is to the top right of your base. Same thing with your log function. The number is to the right of log base 2. Let's practice with part 3. You're going to circle the expressions with correct mathematical notations below. If it's not correct, you're not going to circle it. So please pause this video and give you some time to try to figure out what are the correct mathematical notations below. Alright, hopefully you find out your answers. There are 5 correct mathematical notations. This one, this one, this one, this one, and finally this one. All the other ones are incorrect. For some of them, it's missing the number. Like right here, it's missing the actual number inside of the log function. And for these two, the position of the exponent is incorrect. For this one, of course, the log function is missing the number. For this one, and again, the log function is missing the number inside. Sometimes we can simplify expressions involving logs or exponents by rewriting part of the expression. For example, log base 9 of 81 can be rewritten because 81 is the same as 9 squared. So you rewrite log base 9 of 81 as log base 9 and 9 squared. And then after that, you cross out the inverse operations. So log 9 and power of 9, they're inverse operations. So you simply simplify to 2. Let's look at one example together. Log base 2 of 8. We could rewrite 8 as a power of 2. So if you remember, 8 is the same thing as 2 to the third power. And then we're going to cross out the inverse operations. So log base 2 and power of 2, they're inverse operations. All we have left is simply 3 at the end. So I would like you to complete the rest. Pause this video, work on your own, and then once you finish, restart the video and check your answers. Alright, hopefully you find your answer. So I'm going to go through all of these. Second one, log base 4 of 16. So I can rewrite 16 as 4 squared because 4 squared is 16. And then I cross out the inverse operation, which is log base 4 and power of 4. I got my answer 2. Next one, log base 5 1 over 5. This one might be a little bit tricky because it's a fraction, right? 1 over 5. How do you rewrite 1 over 5 as a power of 5? Well, don't forget that you could use negative exponents. 1 over 5 is actually 5 raised to the power of negative 1. If you figure that out, then it should be pretty easy. You cross out inverse operations, log 5 and power of 5. We got our answer, negative 1. Next one, log base 3 of radical 3. This one is also a little bit tricky, right? How do you rewrite radical 3 as a power of 3? Well, this one you need to use the fraction power for radical numbers. Radical 3, it's square root of 3. It's the same thing as 3 raised to the power of 1/2. Therefore, we cross out log base 3 and power of 3. We obtain 1 over 2 for our answer. And I think last one, you might be able to figure it out. So if you didn't figure out, go ahead, pause the video and figure out what the last one should be. You might get some inspiration from the problems that we just did. Alright, hopefully you are able to figure that out for the last one. The last one, we have log base 2 of 1 over 4. So one thing you could do is first, you could rewrite that 1 over 4 as 4 raised to the negative 1, right? So rewrite that just like number 3. And now we have a base 4, but what we want is base 2. So you rewrite that again. 4 is the same as 2 squared. And then you have to keep the original power outside, which is negative 1. So you have 2 squared raised to the negative 1. And then you apply the exponential rule. Raise the exponent to another exponent. You multiply the exponents. So base is 2, and the exponents will be 2 times negative 1. That's negative 2. Therefore, inside we have 2 raised to the negative 2. And now we are ready to cross out the inverse operations. Log base 2 and then power of 2, they cancel each other out. And we have our answer, negative 2. Alright, very good. Graphing of log. Graphing of log. The general idea is usually we use technology to graph log functions, but if you do really have to graph log functions, there's a little trick that you can use. For example, number 7 right here. If you want to graph this function, y equals log base 5 of x, what would be an easy way to do it? Well, we're going to do the inverse function first. So you're going to graph the inverse first. What's the inverse of this? Well, the inverse of log base 5 is power of 5 and raised to the power of x. This is the inverse function, or let's just make it y equals 5 to the power of x. Last time we did y equals 2 to the power of x. So this is very similar. It's very easy to do it by hand. You just make a list of numbers for x and then plug it in, calculate y, just like what you did for your homework. Once you have this, then you're going to flip the graph across y equals x. Because if you remember from last time, we had a discussion that the visual representation of a one-to-one function and its inverse function, they are symmetric over the line y equals x. Therefore, we're going to use that property to actually graph the inverse first. The inverse of log is exponential function. You graph that, and then you flip it over y equals x, and that's how you get the graph of the log function. So usually, let me just do a sketch. If I do a sketch, this one will be the graph for the exponential function. We have our y equals x. So this is y equals x, let's say. I'm not being super accurate. I'm just doing a sketch. This will be y equals 5 to the power of x. And then you flip it over, and then you should get something like this. So over here, this one will be 1. And over here, this one will be 1. Those are the two special points that you can find. And this red curve is actually the inverse of power 5. So this one is the log base 5 of x. So that's how you graph log functions in general. You could also flip the coordinates like what we did. Swap the x and y coordinates of your exponential functions and then graph them. You will also be able to get the inverse, which is the log base 5. Let's move on to next page. Next page, the most important part is actually example number 2, solving radical equations. So I'm not really worried about this change of base formula. This one, if you're interested, you can remember this, or if in the future you're ever going to take any other math courses that requires you to use the log function, then you might want to use this change of base formula. But for our course, since we're not going to use calculator, so we're not going to use this formula. We will be focusing on solving log equations, like example 2 right here. The equation is log base 3 of x equals 2. We have two ways to solve this equation, so I'm going to show you both ways, and you're going to do that for your homework as well. Let me write the equation right here. Log base 3 of x equals 2. So let's use method number 1. Method number 1 is apply inverse operations. So you apply inverse operations to isolate your variable x. Looking at the left-hand side, you have log base 3 of x equals 2. So you just have to ask yourself, what is the inverse operation of log base 3? So you might remember the inverse operation of log base 3 is the power of 3, which is the exponential function. So I will raise both sides as base 3 raised to the corresponding power. So on the left hand side, 3 is the base and the original left-hand side is the power. On the right-hand side, you do the same thing. 3 is the base, 2 is the exponent. So we have this equation right now. Once you have this equation, then you're going to apply one of the property that we discussed today, which is undo what you just did. 3, that's power of 3. It's inverse operation of log base 3. So you could cross them out. On the left-hand side, we simply have x. On the right-hand side, it's 3 squared. What's 3 squared? 3 squared is 9. And that's it. You have your solution. X is 9. This is method number 1, which is actually recommended if you want, but personally I use method number 2 instead. Method number 2, you're going to use a model to match any log function with an exponential function. Let's say I have a log base b of x, and the value of this is y. Then I can convert this to an exponential function. When you convert it, the base is still the same, so our base is still b. The power of this base b is actually the number on the other side, so b raised to the power of y equals x. These two are equivalent. Now let's look at this problem and see how we can apply this to solve this equation. It's given that log base 3 of x equals 2. That's the log format, and then we're going to convert it to the exponential format. When you convert to exponential format, always start with the base. The base in log function is 3. The base in your exponential function is the same number. So we have 3 as the base. The power of your 3, the base, is actually the number on the other side. In our equation is 2, so 3 raised to the second power. That's on the left-hand side. On the right-hand side, we have x. And then we solve this. 3 squared is 9. 9 equals x. And again, we got our solution. So as you can see, both methods are pretty short, very effective as well. So pick the method that you like the best. If you're not sure, try both methods for some practice problems and see which one gives you a higher accuracy. Then that's probably the method that you're gonna use for your exams. Alright, so let's move on to next page. Next page, we have some formulas. Basically, you derive the product rule for log and the quotient rule for log. The product rule, so I'm just gonna skip the process and give you the formula right away. At the end, we will have log base b of n times n is the same as log base b of n plus log base b of n. The proof basically comes from the exponential property, which is the product rule. When you multiply two exponents that have the same base, you add their powers, and that's basically what this is. The other rule, so this is the product rule, I believe. Yeah, the product rule for log. And the other one is the quotient rule. Quotient rule, instead of multiplying, you divide. If it's quotient, you change the plus sign to minus sign. So you have log base b of n minus log base b of n. And that's the other formula that's very common in log. And of course, there are other formulas in log functions, which could be summarized on the last page right here. Log of 1, so that has to be 0 because any non-zero real numbers raised to 0 will give you 1. Log of b. Log of b is the same thing because b, so let me just explain. This one, the first one is because b to the 0 is 1. So you simply rewrite the log function as an exponential function, which will make it easier for you to understand. For number 2, it's the same thing. This is because when you raise b to the first power, you get b. And all of these problems, you could explain it by using log base b of x equals y. It's the same as base b raised to the y equals x. So rewrite the log function as the exponential function, which will make your life much easier. And of course, number 3 and number 4, those are your inverse properties that we covered. Number 5 and number 6, those are the product rule and the quotient rule that we just discussed on previous pages. Number 7 is the power rule. So it says that log base b of m raised to p, you could actually bring that exponent p to the front, and that becomes p times log base b of m. So that's also a very popular formula that you might use. And lastly, we have that change of base formula, which in this course is not very important. Very good. For today's homework, just like last time, I added additional pages to the end of this page. So if you printed out the PDF, you will not have these pages. Make sure you manually look at these 2 pages when you do your homework. We have basically 2 types of problems. One type of problems are solving log equations, and the other types are solving more complicated log equations. Some of them are exponential equations. So I'm gonna go through number 1 and number 3 on the second page right here to demonstrate how you could solve some complicated exponential equation or log equations. Number 1 right here, the base is 4 raised to the power of 2x minus 3 equals 64. To solve this, I highly recommend that you rewrite both sides as the same power, same base, at the same base. So what I meant by that is, for the left hand side, I'm gonna keep it as base 4 raised to the power of 2x minus 3. On the right hand side, 64 is actually a perfect cube. It's actually 4 cubed. So if you're not convinced, you can actually multiply 4 by 4 by 4, you will get 64. Notice that I converted both sides to the same base, 4 and 4. And from last class, we know that exponential functions are 1 to 1, meaning that for that one base, it's corresponding to one output. Therefore, you could guarantee that the exponential part, that 2x minus 3 and 3, they have to match exactly. So we have 2x minus 3 equals 3. You converted an exponential equation to a simple linear equation. So you simply solve that for x. Move that negative 3 to the other side. We have 2x equals 6. Divide both sides by 2. X is 3. So we have our solution to this problem. So for number 2, you're going to follow a similar way to solve. Let's look at number 3. Number 3, we have a sum of 2 log functions equals 3. This one, you have to apply the product rule right here. On the right hand side, if you add 2 log functions that have the same base, you simply multiply the numbers inside. So that's exactly what we're going to be doing. We have the same base, which is log base 4. As for the numbers inside, by product rule, we're going to multiply the numbers. So x times 2, that is 2x, equals, the right hand side is 3. And then this just becomes a log equation. I'm going to use the equivalent form to solve this, but you're welcome to use inverse operations if you want. The equivalent form is I rewrite this log function as an exponential function. Remember, the base is still the same. The base of this log function is 4. So the base of my exponential function is also 4. The power of my exponential function will be the number on the other side, which is 3, equals, and then you write down 2x on the right hand side. So this is the new equation. We converted the original log function to, we converted the original log equation to an exponential equation. Now let's solve this. On the left hand side, 4 cubed, we just discussed this, is 64 equals 2x. And then I divide both sides by 2. I got 32 equals x. And that is my solution to this one. Let me actually move this a little bit up so you could actually see the problems. Very good. Hopefully you learned something today. And that concludes today's lecture. The homework are these 2 pages. Make sure you finish these 2 pages and upload to OneNote. And thanks for watching.